nomine Patris et Filii et Spiritus Sancti. Amen. Veni Sancti Spiritus, repletorum corde fidelium et tui amoris in eis ignem accende. Imite spiritum tuum creabuntur, et renovabis faciem terrae. Oremus, Deus qui corde fidelium Sancti Spiritus illustratione docuisti, da nobis in eodem spiritu recta sapere et eius semper consolatione godere, per Christum Dominum nostrum. Ave Maria, gratia plena Dominus tecum, benedicta tu in mulieribus, et benedictus fructus ventris tui, Iesus. Santa Maria, Mater Dei, ora pro nobis peccatoribus, nunc et in hora mortis nostrae. Amen. Sancte Roberte, ora pro nobis. Sancte Piedecime, ora pro nobis. Sancti Philippe et Jacobe, ora pro nobis. In nomine Patris et Filii et Spiritus Sancti. Amen. Okay, so here's a chemistry video about the activity series and ionic equations and what this all means. The activity series is a listing, basically, of reactivity. It's a way of explaining which elements are more likely to combine with others and helping us to tell in what situations reactions are going to actually occur when I combine certain elements or certain compounds. And this is listed in a chart in your book on page 210, but I've tried to reproduce it here. It's a little bit long, so I had to go vertical, so this may not all fit on screen at the same time, but we'll try to scroll up and down as I talk about the different categories. So basically the series here is ordered from most reactive elements at the top. Okay, the ones that have the highest activity, that are most likely to cause a chemical reaction or to combine with something else, to least reactive. Down here at the bottom with the element of gold, actually. And there are two separate series. There's one for the metals, as you can see here, and the metals also includes hydrogen. We've discussed before how hydrogen is actually a metal, technically speaking. So it's included in the activity series for the metals, and then the halogens for the halogens. You have an activity series amongst them. And basically for the halogens, it's just based on electronegativity. So the fluorine, obviously having the greatest electronegativity, is going to be the most active, the most reactive. Chlorine is second, then bromine, and then iodine is the least reactive of the halogens. So in other words, if you combine some salt or some other chemical with these various halogens, if you mixed in, like, say, some fluorine gas and some iodine gas with another compound, the fluorine is going to replace or react with the elements in that compound before the iodine will. And in fact, the iodine will probably not react at all because the fluorine is present. Same things with the metals. If I put some lithium and some calcium in water, the lithium is going to react more violently, more strongly, and it's going to use up or bond to the water or form compounds with the water before the calcium will. It doesn't mean the calcium won't. It just means the lithium will sort of be used up first, and then the calcium might proceed to react. Okay, because the lithium is higher in the activity series. So we can use this to judge whether reactions are likely to occur or not when I mix certain things. And these different categories here are just kind of their general sets of these elements, which, due to the degree of their reactivity, are able to react with different compounds. So the least reactive ones will form oxides in some cases. Okay, so silver, gold, mercury. These will oxidize, they can, but it's indirect, and in other words, it doesn't require only the presence of oxygen to form an oxide from these in order to react. You need oxygen plus something else has to be going on. Okay, there's some other kind of energy condition or something that will allow that oxide to to form. And this is the reason why gold is, in fact, so inert, and it's valuable. Part of what makes it valuable is the fact that gold does not oxidize. Gold does not react with very many things, or under normal conditions, it does not react, at least. And so you can have a gold coin that was minted hundreds of years ago, and 500 years later, even after sitting at the bottom of the ocean or sitting out in the air or being buried, okay, wherever you put it, it's still going to pretty much be as shiny and have the same luster and polish that it did when it was lost or when it was left behind. So gold doesn't really tarnish like the other metals do. Silver is not super reactive either, but silver does oxidize and it does tarnish and needs to be polished more frequently than gold. Elements that are slightly more reactive, like hydrogen and copper, well, these will react with oxygen under normal conditions. Okay, so if I have some hydrogen gas, or I have a piece of copper, or a copper statue or something, it will react with the oxygen in the atmosphere under normal conditions, and it will oxidize. Okay, with copper, you get that green scale that develops all around the outside of the thing and turns it greenish or bluish green. That is copper oxide, in fact. The next set of more reactive elements, more active, they will react with acids. So if I put them in acid, the acids will form salts or something with them, and hydrogen gas will be released. Okay, this is what it means by liberating hydrogen. Even more reactive metals, magnesium, aluminum, manganese, zinc, chromium, iron, and cadmium, these will even react not only with acids, but even with water in the form of steam. So it's not just any water, it's high energy water. It's water that has a lot of kinetic energy. So it's in its gaseous phase as steam. These will react with water directly. And again, they will form some sort of salt or a base, or a salt or a base, and hydrogen gas will be freed from the water. Okay, and then finally, the most active metals like sodium, we've seen videos of sodium and potassium where they were throwing a chunk of that element in the water, and it reacts very violently. It releases it pops and spits and blows chunks of sodium all over the place, and kind of burns just from the contact, even with cold water. And part of that popping and spitting that you're seeing, and that's from the gas that's being released, the hydrogen gas that's being formed from the reaction of that metal with the cold water. Okay, so depending on how reactive they are, how high they are in the activity series, they will react with more substances or less substances, and under fewer conditions or under more conditions if they are less reactive. So let's see how we can actually use this in practice. Okay, here are some examples. First of all, these three equations are examples of situations where the activity series comes into play, and you will have a replacement reaction. So we are mainly looking at replacement reactions, either single replacement or double replacement reactions when we're talking about the activity series, and we have some of those here. The first one is a famous experiment that I usually like to do in a normal year. I would do this in class, and we would do this together, and you would see how this works. Since we can't do that, this silver tree experiment, I will post a link to a video in the description, which you can follow and you can watch if you're interested in this. It's really a cool reaction and quite beautiful, in fact. So if I have some copper, some solid copper, like maybe from a penny or a little piece of copper wire from electrical wiring, and I put that in a solution, of water and silver nitrate to AgNO3, aqueous again. When you see this means it's dissolved in the water, it's in solution. So if I put copper in that solution of silver nitrate, the copper is going to actually replace the silver. And the reason the copper replaces the silver and you get copper nitrate in solution, and the silver, it comes out as a solid, so it actually precipitates. And what it does is it forms little silver crystals on the copper item that you put into the solution. And so you get these little crystals that grow all around the copper, and it looks kind of fuzzy-ish. And eventually it starts to look kind of dirty, and they start to clump and fall apart, and they don't look so much like crystals anymore. But when they are first growing, you can see clearly that they're forming these little crystal sort of spikes of silver. They look like little hairs almost. And the reason that this will happen, okay, that the copper will replace the silver and bond to the nitrate, or will associate with the nitrate and take the place of the silver, it will replace it, is from the activity series. If we look at the listing of the elements in the activity series, you can see that we have copper way down here, and then silver here. And so copper is just a little bit higher in the activity series than silver is. So it will associate more easily with the nitrate. And in fact, it will replace the silver. It will take its place. And the silver will be left with nothing to bond with. And so it will just fall out as a precipitate and form its own little crystals of pure silver. The second reaction is putting sodium in water. Okay, so again, an alkali metal, we're just throwing it into the water, and it's going to react, and it's going to release, again, hydrogen gas, as we saw in the activity series, which is what you see as one of the products here. And then the sodium is going to bond with the other part of the water molecule, other than the hydrogen that's released. It's going to bond with the hydrogen and the oxygen that's left, which is actually going to be, at that point, a hydroxide ion. So you're going to form sodium hydroxide, which is a very strong base, which is going to be dissolved in the water that's left. And then the hydrogens that were released, that were replaced by the sodium here. So this sodium is replacing one of these hydrogens and bonding with the remaining hydrogen and oxygen, or associating with it, I should say. The remaining hydrogens are going to be released. They're going to bond together and be released as bubbles of hydrogen gas. And again, if we look at the activity series, this will show us that this is a reaction that can occur and is likely to occur because hydrogen is way down here on the activity series, and sodium is quite high in the activity series. So it is very likely that sodium will replace hydrogen in a given reaction. Okay, and then the last example, we have a double replacement reaction this time. Lead nitrate in solution plus potassium chromate in solution yields lead chromate, which is going to fall out as a precipitate, and potassium nitrate, which remains in solution. Okay, and so there's two things being replaced here. And so in a double replacement reaction, you kind of have to think about the activity series for both sets of elements that are swapping, or sets of particles that are swapping. Lead and potassium in this case, it's pretty clear that potassium is, again, much higher in the activity series than lead. In fact, it's the second most active of all the metals, and lead is not that active. So the potassium is going to combine with the more active of the two negative ions. So we have, in these compounds, when they're in solution, we have the nitrate ion and the chromate ion. And I haven't given you an activity series for ions like this, oxyan ions, but in general, nitrate is a pretty active ion compared to chromate. So the potassium is more active than the lead, and the nitrate is more active than the chromate. So the potassium and the nitrate, being the more active particles, are going to associate together, and then the lead and the chromate, being the less active, are going to sort of be left. Well, okay, there's nothing else for us to bond with here. These active guys, they wanted to associate with each other more than we do, but there's nothing left for us to associate with. We don't really have a choice, so these two will combine to form lead chromate, okay, the two that are less active. Okay, but it's driven, though, by the more active elements. It's driven by the fact that potassium is active and the nitrate is active, and they will then tend to want to associate with each other because, again, that's going to give them a lower energy configuration, and they will be able to be in a lower energy state in that situation because of their high activity. Okay, so we can use this we can use our activity series chart to predict whether reactions will occur or not. So if I, for example, if I take some barium and I throw it in some water, will anything happen? Will the barium combine with the water and replace, say, the hydrogen in the water or not? And so to know the answer, I will go to the activity series and I will compare the two. Barium is third from the top in the activity series. Hydrogen is quite low on the activity series, which means that the barium will almost certainly replace the hydrogen in this situation. If I combine these two things, there is going to be a reaction. The barium is going to take the place of the hydrogen. And so what we're going to get from this situation is the barium is going to take the place of that. So you will form barium hydroxide, most likely in aqueous solution. And then you will have, again, hydrogen gas as a byproduct. Hydrogen gas being released. Okay, another situation. If I combine barium with tin chloride, okay, will anything happen? Well, again, I go to my activity series. Barium is highly active. Tin is not so highly active. So probably the barium is going to replace the tin here. And in fact, it will. So these are going to swap, and the products will be barium chloride. So the barium will combine with the chlorine, being more active. And then the tin will be left just to fend for itself. And so you will just have solid tin, well, precipitate as a result. Okay, again, this is probably, most of these happen in solutions. So whenever you have a solid product, it's going to usually be dropping out as a precipitate. Gold, if I add gold to table salt, sodium chloride, does anything happen? Well, gold is the very least active of all the metals. And sodium is highly active. So is a less active metal going to replace a more active metal? No. The answer is no. The gold will not replace the sodium here. So actually nothing will happen in this situation. There will be no reaction. The gold is not active enough to sort of push the sodium out and take its place with the chloride. Zinc and sulfuric acid. I go to my activity series. Zinc is about in the middle. Sulfuric acid is, well, it's sulfate and hydrogens. So we're looking at hydrogen here in comparison to zinc. So zinc is more active than hydrogen. So this reaction should occur. The zinc will take the place of the hydrogen. And so you'll get zinc sulfate plus, again, hydrogen will be replaced and released. So you'll have hydrogen gas as a byproduct. Chlorine gas plus magnesium bromide. Will this reaction occur? Well, here you have, the difference here is we've been doing all metals up until now. Now we have a situation where we're comparing halogens. Okay, we have to compare chlorine and bromine. And chlorine is more active than bromine. So the chlorine will tend to replace bromine when it can. So what's going to happen here is the chlorine is going to sort of take the place of the bromine, kick it out, disassociate it from the magnesium, and it's going to associate with the magnesium itself. So this reaction will occur, and you will get magnesium chloride, and then bromine will be left by itself as bromine gas as your products. Okay, and then the final example, again, is with halogens, iodine and magnesium chloride. Iodine is less active than chlorine, so in this case, no reaction will occur. The iodine is not able to push the chlorine out of its association with the magnesium. Okay. That gives you some example of what the activity series is about, and I'll make a separate video, since this one's getting a little bit long, I'll make a separate video about ionic equations and spectator ions.